Hello everyone, today we're going to be going over a differential energy balance, and we're going to be explaining and deriving it in the heat diffusion equation for cylindrical coordinates. So to first start, we're going to have our cylinder right here, and we will have heat going in versus heat going out. So to and then this will be over a length of c. So to kind of get a feel about that, on how it would look in a graph kind of sense, we will have an angle with a theta value, and then this will be translated to a differential theta value, d theta, a length of z, which will put that of dz, and then z, and this will go over a length of r, dr. So we kind of get a 3D picture of this. Don't mind my artistic skills, not the best. So that's kind of what our picture will kind of look like. But an important key aspect to note of this is on this theta value, that is just an angle, right? So we need to be able to translate that to an actual number because we can't take a derivative of a theta. So this theta value, to get that and to translate into our volume, we're going to use that r value, r d theta. So r value times the theta is equal to that length. So to get our volume, then it would be r d theta dr dz. That's our volume. So now we're going to recall those past equations that we were working with when we were working with our Cartesian coordinates. So we have our energy generation over volume, with respect to volume, we have our heat generation, Q value, Q dot value, times volume, which, as we just explained, is R d theta dr dz. Now we have our heat equation, which we'll denote by that E rate and then that ST. And this is heat capacity, or density times heat capacity, times the derivative of temperature with respect to time, and then again times our volume, which, as we just explained, is that R value d theta dr dz. So now we're going to try to find our net heat flows at all three angles, which is dr, d theta, and then dz. So we'll start by using the Taylor series expansion. In part one of this series, I kind of explained how to do the Taylor series expansion, so if you want to go check that out. But I will just write a little reminder that that's what we're using here to estimate the slopes at those specific angles that we don't know. So for a reminder, we have our Q value of dz, and this is estimated to be qz plus our derivative of qz over dz, and that dz value is evaluated at z and times dz. And our net heat flow is equal to qz minus qdz. So to input that qdz now from our estimation, and then we can cancel these terms out and then simplify this. Negative dqz over dz times dz. So now we're going to do our R value. So our estimate at QDR is QR plus DQR over DR. But DR is evaluated at R, and times DR. So our net heat flow, I should probably put Z here, just so we know what we're talking about. There's no confusion. It's QR minus QDR. And putting that equation in, QR minus QR plus DQR over DR, and DR divided by R times DR. Cancel these out, simplify. So we have negative DQR over DR times DR. Now our last one is our theta. So we have our theta value, net heat flow, our estimation that Q d theta is roughly Q theta plus dq theta over d theta, and that's evaluated at d theta is equal to theta times d theta. So our net heat flow is equal to q theta minus dq theta, qd theta, and putting that equation, so cancel those out, simplify this down. So we'll have negative dq theta over d theta times d theta. So now that we have those net heat flows, we're going to try to remind ourselves of what the big equation is going to look like. And then I'm going to erase this, and we're going to get into Fourier's law and how it relates. So our big equation again is a heat equation is equal to net heat flow of Z plus net heat flow R plus net heat flow. That does not look like an R. Theta, and plus our energy generation with respect to volume. So I'm going to erase this real quick, and then we're going to relate this back to Fourier's law. All right, so now we're going to relate back to Fourier's law here. So if we remember what Fourier's law is, Fourier's law is that Q value, that heat, times our thermal conductivity, times our area, and then our derivative, we'll say this is R value, dt over dr. So our derivative of temperature with respect to that R value, or radius, whatever. So, what is that A value? If it's an area, we're going to be remembering that it's dz, as it's heat flow coming in from here, right here. So I'll move out of the way, just so you get a better view. So you have heat coming in from this angle, right? So what is that? It's the arc length times that d value. So it's coming, drawing the wrong area. It's coming in from this angle right here. So it's arc length, which is this value right here, and then times that dz, as it's coming in through this way. It's coming through that dr. So that area is then for QR, let's try AR. So AR is equal to R d theta. If you remember, we had that R value there times that theta, because we can't multiply it by just an angle. And then times dz. So putting that back in, we have QR times negative K, and R d theta, dz, and then dt dr. Now for our z value, we have qz, negative k, az, dt, dz. So, same kind of scenario where our, where our heat flow is now coming in either from top or bottom. It's going like that. It's coming down, so it's going through that dz value. So the area that it's going through is at dr and times the d theta. So the area of z is again that r value times d theta, because we can't multiply by just by like degrees, and times dr. So plugging that back in, we have qz, we go to negative k, r d theta times dr, and then times derivative of temperature with respect to the z value. Now, lastly, we have net theta. So q theta times negative k, a theta, and then dt, r d theta. So the reason we have that r there is because, again, we want to be in Cartesian coordinates here. And we can't take the derivative of just a theta value. So we put that r length in there to make it like an earth length. So that way we can get this all in kind of the same kind of units. So that a theta, nothing weird about this one. We just have dr times dz. As again, heat flow is coming through the arc length, which is r value times dz. So our q theta is negative k dr dz times dt r d theta. So now we can plug that back into our big equation and we'll break that down. So it's going to be a lot of writing right here. Put like a little line, just so we know exactly where we are. So if you remember what our heat equation is, we have density times heat capacity times our derivative of temperature with regard to time, and times our volume, which was r d theta dr dz. And we have net heat flow of z, which if we remember correctly was negative dqz times dz over dz. And then, so we have minus negative dqr times negative dr times dr. And then we have minus dq theta over d theta times d theta. And then plus our q value times dr, d theta, dz, and times r. So that's our big equation right there. So now we can input these q values into where we see fit. So we put equal to negative d dz, and then times, we have our negative k value, times our area for dz, which is r d theta dz, or no, not dz, dr, sorry. Yeah. And then we have our derivative of temperature with regard to z times dz. And then for our q value, we have, again, negative dr value, and negative k. And then our area for r, which was r d theta times dz. And our derivative of r, our derivative of temperature with respect to r, and times dr. And then we have our d over d theta, our negative k value, our area, which is d theta, or dr times dz, times dt r d theta, and then times d theta. And then lastly, we have our heat generation, which is that Q value, that heat generation times our air, or times our volume. So there's our big equation right there. It's kind of broken up into two. As we have our dz, our dr, our d theta, and then our heat generation, or net heat flows, excuse me. So we can do some simplification here, as we can cancel out all these d theta, dr, dz's. We're going to leave that r alone for now, and we'll deal with that here in a second. As for some of those drs, it's a little bit tricky. So our simplified equation will look like this, as we have our density times heat capacity times derivative of temperature with regard to time times r, and that's going to be equal to, and then we'll also, all these can become positive as well, so it's double negatives. We have our d dz times k times r times dt dz plus d dr times k times r times dt dr, and then we have plus d theta dd theta over k times 1 over r times dt d theta, and then plus heat generation times r. So now we're going to go over this r value and what to do with it. So we're going to cancel out this r, so we're going to divide by r, but for some of these it's going to be a little bit weird. And then additionally, at the same time, if we remember what our thermal diffusivity is equal to K over density times heat capacity. So we're going to try to separate out that derivative of temperature with regard to time. So going back, we have d dz, and then that r values will cancel out, and then we have our thermal diffusivity, and actually I'm going to put it like this. So I'm sure you can kind of see what we're gearing up to do. So with this r value, we're actually going to leave it inside because it's a derivative of r and it could be affected. So we're actually just going to leave these two separate. They're not going to cancel. And then for this r value, we can take that out of this one. So we'll have and then these r values cancel on the heat generation, but then we have the heat capacity and density coming over. So now we can just make these into the second derivative. And if you remember, this looks very familiar with some slight changes in the r values to our equation for the Cartesian coordinates in a three-dimensional area. So there's our equation. I'll make this look a little bit nicer by combining a lot of these terms. So we have theta value, and then dt, dc, 1 over r, dt, dr, is r. So there is our final equation for heat diffusion for cylindrical coordinates. And I'll make a little circle around it. So again, it looks very similar. You have the r values. You have this 1 over r squared and then 1 over r in the r value. So it's a little bit different in some areas, but it's all in together very similar to our other three-dimensional shape. Thank you very much. Hello everyone, so today we're going to be simplifying our expression that we just derived into a steady state with no heat generation and then flow only in the radial direction. And we're going to yield this expression to relate it to the equivalent thermal resistance that's equivalent essentially to electrical circuits. So first, let's recall our equation that we just derived. So we'll start with our dt, derivative temperature value in respect to time. It's going to be equal to our thermal diffusivity. And we'll start with our z direction, which is our second derivative of temperature with respect to our z value, and then plus 1 over r times our second derivative of temperature in our radial direction, and then times r, and then plus 1 over r squared, our second derivative of temperature in regard to the theta position, and then plus our heat generation. So, first of all, we have steady state, so this can be marked to 0, and we have no heat generation. Additionally, we're only in the radial direction, so we can get rid of our z value, our temperature derivative in respect to our z value, and our temperature derivative in respect to our theta direction. So, our new equation will look like so. Where we can also divide out this thermal diffusivity as it is in steady state. So we don't really have to worry about this. So we have 0 equals 1 over r. And then we're actually going to expand that out a little bit. So we have d dr times dt dr times our r value. So this is our new expression that we have right now, as we no longer have our different directions, our heat generation, our thermal diffusivity, and we are in steady state, so it is equal to 0. So how can we solve this? First, we're going to introduce a constant integration, which will be equal to r d dr. So our new equation looks like c over r dt dr. So now we can set these equal to each other. C over r is equal to dt dr. So now we're going to integrate both sides. Sit down for this. We can multiply both sides by dr, which will get us dt by itself, and then we'll have CR times dr. So now we can integrate both sides. So we'll have T final, T initial, dt is equal to C. That'll be outside our integration because it's a constant. And we'll have R final, R initial, we'll have 1 over R dr. And that will get us T final minus T initial is equal to our C value, and then we have ln of Rf minus ln of R initial. So we can use our natural log rules right here. I'm going to draw a big arrow up here to where we can simplify that. So we have T final minus T initial is equal to C value ln of R final over R initial. So now we can separate that T initial over to the other side. Or actually, we'll divide out this ln. Jumping ahead, sorry. And we will get that C value, that constant integration value by itself. So our C value is equal to our temperature final minus our temperature initial, and then the natural log of the radial final over the radial initial. So we can plug this back into our original derivative and see what we come out with there. So we're going to set up our derivative a little bit different this time, as we will have just T, our temperature, and then our temperature initial of dt. We have our C value, constant of integration, and then we have our R value, our initial, and then we have 1 over R again. We'll take this out again, as we have temperature minus temperature initial. We have our C value, and then again, we have our natural logs. So draw another arrow up here. We can input that C value back into the equation. Make sure you guys see that. And so we'll have our temperature initial equal to our C value, which is T final minus T initial over natural log of radial final over radial initial, and then times natural log radius or natural log of the radius initial. So now we'll be back. We can use our natural log rules again, as well. Temperature minus temperature initial, temperature final minus temperature initial, our natural log of R final over R initial, and then we'll have natural log R minus R initial, or over R initial, excuse me. Now we can add that over, and our temperature is equal to temperature final minus temperature initial, natural log of radial final over radial initial, times natural log of the radius over radius initial, and then plus the initial temperature. So now we can put the C back in here, as well. Temperature C ln R over Ri plus Ti. And we'll take the derivative of all this. So we'll have dt dr. That constant stays. And then we'll have 1 over R initial, and then R over R initial, And then this is just 0 because we're taking a derivative of it. So you have this value, and then we can put back in our C value, which, again, if you remember, is T final minus T initial over ln Rf over Ri. And then we have 1 over Ri, and R over Ri. So there's our dt dr value. And I'm going to move all the way back over here. I'm going to write in a different color, just so we are clear about where we're at. So now we're going to relate this back to our original Fourier's law. So Q is equal to negative thermal conductivity, area, and then derivative of temperature with respect to the radius in this instance. So what is that area? Area is 2 pi r, as we are doing with the circle. So we have that. So now we can input our dt dr, as we already know what it is from over here. So our Q value is negative k 2 pi r initial, and then our dt dr, we have T final minus T initial over natural log of R final over R initial, and then the brackets on that, 1 over R initial, and then R Ri over Rf. So there is our Fourier's law recall. So now we can actually do some canceling here with our Fourier's law. These Ri's can go away. This R value can go away. So now we can simplify this a little more, as we have our Q value is equal to negative k 2 pi. Actually, I'm just going to clean that up a little bit. And then we have temperature final minus temperature initial. And then we have our ln value of Rf for Ri. So, if you notice here, we are now at our final Fourier's law makeup. So now we can start trying to relate it to Ohm's law. So I'm going to erase a little bit here to kind of get a clear path of where we're going with this. So, what is Ohm's law? We recall Ohm's law. Ohm's law is delta V equals IR. So, we have a temperature final minus temperature initial. Temperature final and temperature initial, that is equal to delta T. So we have our delta T value. So if we want to set these equal to each other, we have Q negative K 2 pi delta T, and then we have ln R final minus R over R initial. So we have our delta T. We're going to set that equal to the other side. So we have delta T Q ln Rf over Ri, and then all over negative K 2 pi. So we have our delta V's matchup and delta T's, our Q and our I matchup, so our current matches up. So now what is our resistance? Our resistance is negative natural log of R final minus over R initial over K 2 pi. So that is our resistance in this equation. However, we are actually missing something. So it's very important in this that we add in height. So height would go on the bottom right here, because we don't want to miss out on height, because height is very important to this equation and how it is moved in the radial direction. So our resistance is actually natural log of our resistance, our radial final over radial initial over thermal conductivity, 2 pi height. So thank you very much. That is our resistance.